The first unit, what is the first unit? Orbital mechanics. And the first specific topic is circular orbits. We're going to start with the basics, and over the next 2 weeks, we learn all of the astrodynamics that you need to be an electrical engineer that does something in space. You can spend an entire career studying this stuff. If you were an aerospace engineer, how many courses in orbital mechanics do they offer at the graduate level in aerospace now? 2 or 3? 2? Okay, so it's a 2-semester sequence. 2 weeks, and we pass the savings on to you. But you'll know enough to talk with an aerospace person. You'll know all the terminology. But first, let's put a couple of historical dates. You'll notice on some of my sample tests, I even ask about some of the key historical dates in satellite engineering. The first one I like to put up is 1945. This is long before we put a spacecraft or anything into outer space. But this was an important article by the science fiction writer Arthur C. Clarke. But this is actually a technical article. He wrote an article called Extraterrestrial Relays. In Wireless World magazine or periodical. And his idea was radical at the time. He says, you know, if we could put a radio in space, you could send a signal up to the radio and it would bounce back to another part of the Earth. And that part could be beyond the horizon. And you would still get the signal. That was actually a pretty radical idea in terms of radio communications back then. The only way to get signals beyond the horizon from a communications standpoint at this time, you could use the telegraph, or you could bounce a signal off the ionosphere. Anything like 1 megahertz or less bounces off the ionosphere because the charged particles are dense enough for those low frequencies to act like a perfect electric conductor. And they bounce the signal to another part of the Earth. The problem is you don't get that much bandwidth. And of course, there's only a certain amount of spectrum available. If the entire Earth has to reuse that same spectrum for its bounces, then it becomes a very cluttered radio channel indeed. And of course, the telegraph isn't a very convenient way to send information either. In fact, we're still, believe it or not, I don't know if you believe me, but we're still basically doing the back in 1945. It wasn't until the 50s that we had the transistor, and that could actually do analog voice from one continent to the next, like from New York to London or something like that. The first telegraph, the kind of telegraph, was deployed in the 1860s. That's when they laid the cable. And it took until the 50s, because there was really no way to regenerate the analog signal reliably under the sea. You couldn't even do it with tubes, right? You can't exactly change the tubes out if they burn out at the bottom of the ocean. And so, that our options were very limited back then. And so this was a radical technology for sending signals beyond the horizon. Now, we use satellites for a lot of different things nowadays as well. We use them for surveying, we use them for geolocation, navigation systems. But this was the captivating application that began the race for space. And this was a big problem back then. The U.S. was even funding a lot of research around this time to use things like moon bounce communications. So we wanted to spy on the Russians, right? So how do we do that without a satellite? We use the natural Earth satellite to do it. If the moon is in the right spot, the signal goes up, bounces off the moon, and comes back down. But it turns out there's a lot of problems with detecting signals that way. It was interesting. Now, Then what happened in 1957? Anyone? Almost 60 years ago. First satellite, which was called Sputnik. And that forced America to get its act together, and the next year we launched Explorer 1, and the space race was on. That's the first U.S. satellite. And then later that year there was another satellite called SCORE. First one was Explorer 1. SCORE was the first one to actually transmit a voice broadcast. It transmitted President Eisenhower's State of the Union address at that time. And these were all low Earth orbit satellites, which we'll get to what that means in a second. And then in 1962, Bell Labs launched the first commercial communications satellite, Telestar 1 and 2. It's actually 2 satellites. And this became sort of the template for the next several decades of a classic architecture, the classic analog bent pipe architecture in satellite communications. It had an uplink of 6.389 gigahertz and a downlink of 4.169 gigahertz. And solar batteries, and it had a single transponder on it. It didn't have the multiple ones that would come later. This is really the first commercial launch of space. And then in 1980, you had some of the first GPS satellites go up, satellite system that they had been working on in the late 70s. And this is one of the big innovations in navigation, and in fact would be so pervasive that we use it to this day still and take it for granted. It's on every phone you've got. It's in bank ATMs. It's in all sorts of crazy things that want to do time and space positioning very precisely. And usually after we've covered everything in this class, we start off with astrodynamics, because you got to understand where your radios are going to be in order to communicate with them and what the limitations are. Then we move into antennas and propagation. Got to figure out how to send signals to and from a device. Then we get into telecommunications, and then at the end of the course, I usually spend time working through how GPS works. The last week is geolocation using GPS, just because it's such an elegant synthesis of all the pieces that we learned up until that point. So the GPS launches at 1980. And then in 2000, you had a lot of low Earth orbit, LEO, low Earth orbit satellite systems launched, like Iridium, Global Star, Orbicom was another one. These are constellations of 60, 70, 80 low Earth orbit satellites that are providing global coverage to anyone with a personal handheld handset. And I could probably put some more dates on here. I'll cut it off here, but you know, some of the recent things that have been going on in space, we've got the privatization of space. You know, private companies actually handling launches instead of governments. That's actually a big deal. The cost of launch is coming down. Some other interesting historical things are happening. Actually, one of the things I've gotten a lot of phone calls about recently, recruiters from Google and some other companies that want to put CubeSats into space. A CubeSat is a small satellite that has these standard dimensions that go up in payloads that become a very popular platform for launching little satellite projects. Somebody wants to launch CubeSats into outer space and take a picture, do surveying, take a picture of the Earth, every square inch of it, every day. So you have this massive database of what the Earth looks like every day. Kind of creepy, but interesting. Cool communications project, cool satellite project. So I'm even wondering, I'm getting so many recruiting calls, I'm wondering if maybe that should be our project, to design that system for them, for free. For free. Okay. Now, this is the part where you got to do some math. I'm going to take you back to your freshman or sophomore physics class, and we're going to build our understanding of orbital mechanics from the ground up, which means we've got to start with Newton's law of gravitation and good old F equals ma. We're going to first start with the simple stuff. I'll derive the kinematic equations. We'll look at the special case of circular orbits, and once we're comfortable with that, we'll move to what an elliptical orbit is, which is the general case of a stable orbit around another body. And we'll do that by introducing Kepler's 3 laws. And basically, we'll be building the terminology that we need to talk about all the orbital mechanics that you need as an electrical engineer to talk about a satellite in orbit. So, let's start at the beginning. Okay. In Newtonian gravitation, I've got 2 masses always. There's mass 1 and mass 2. And they're separated by a distance r. Call r the separation distance. And if these have masses, they are going to mutually attract one another. There's going to be a force on object 1 due to mass number 2, and a force on 2 due to mass number 1. And they are going to be equal and opposite. Equal in magnitude, opposite in the direction. Their magnitudes, F21 is equal to F12. And the formula for this, if you remember from physics, is G m1, m2, the product of the masses, times this magic gravitational constant, which is 6.672 times 10 to the negative 11th, and that's units of Newton meters squared per kilogram squared. And then divided by r squared. This is a 1 over r squared law, like so many other field equations in physics. So that's how we start. That's how we start. Now, Newton also came up with some pretty sharp things to say about the motion of objects. So Newton's law of motion, one of the bedrock concepts in physics, F equals ma. Force is equal to a mass times an acceleration. My high school, you knew you're at bedrock physics. My high school English teacher put this formula on the board and called it Newtonian mechanics. And one of the students raised the hand. And they said, well, could you explain what this means again? And the professor kind of looked at it and he said, well, you see, F equals ma. I'm not sure you can really give a better description of it, right? This is how it works. This is the world. And so it kind of cracked up the class a little bit. But F equals ma. And the interesting thing about this is that even though we kind of present these as 2 completely different formulations, Newton's law of gravitation and Newton's law of motion, it's interesting that they use the exact same masses. in one another, and that if you equate them, one of the masses drops out, the mass of the moving object. And so, even at this point in time, this was actually one of the hints of the idea of general relativity. It just so happens that these masses are the same, and they always drop out when you put them together. And so that the object is left with just this intrinsic property of space and its own mass, or the mass of the object nearby that is influencing its motion. And so let's go ahead and work through that quick exercise. If every force makes an acceleration, then let's say I want to study the movement of mass 1. In this system that I've drawn over there. If that's true, then m1 times a1, acceleration of 1 times mass of 1, should be equal to g m1 m2 r squared. Of course, the masses cancel, and the acceleration of body 1 is only due to the presence of the mass of the object number 2. And that's a profoundly simple result. Now, we're engineers, so we have to do this rigorously. I've drawn everything as scalars at this point. To really understand orbital mechanics, we're going to have to move into a vector representation. And so here's the convention that we're going to use to talk about orbits in this class. We're going to have an origin. And it is more convenient at this point to work in the cylindrical coordinate system instead of the Cartesian coordinate system. So instead of describing an orbit in terms of x and y, I'm going to use r and theta. And that is actually the physics and mathematics convention, not the electrical engineering convention, because most of this stuff comes out of physics and mathematics books. Electrical engineers haven't written that much about orbital mechanics. If we were doing the cylindrical coordinate system, it would be what? Rho and phi. That's how electromagnetics engineers talk about these things. So this is r, and the angle that you would make with what normally would be the x-axis in the Cartesian coordinate system, that's what I'm going to call theta. So this point in space, if I describe it as r and theta, that will describe in a two-dimensional space the trajectory of my orbit, r as a function of time and theta as a function of time. Okay. Now, everything that I'm going to draw on the board is going to be two-dimensional without loss of generality, right? Because if I have a planet and I got a satellite orbiting around it, there is a plane that's going to contain both the centroid of that planet and all the points on the orbits. I may have to tilt the plane and do some crazy twisting with it, but there's always a plane that I can normalize the problem, and that greatly simplifies everything, the math of the analysis. In fact, when you do homework number 1, which I'll assign probably early next week, what you'll be doing is doing a 2D code, and then when you're finished tracing out the orbit, you're going to twist and tilt it up until it's inclined, and then actually do a sky track or a ground track of the orbit, the track that it makes along the Earth, and then the track that it makes across the sky, which is ultimately where a lot of this analysis is going. We're electrical engineers. We want to be able to point antennas to our satellites. How are we going to know where to point them if we don't understand our orbital mechanics? And so that's one of the key questions that we want to ask at the end of this. So don't get too bogged down with the mathematics. There's light at the end of the tunnel. Okay, so my trajectory is a pair of coordinates, r and theta, and they are going to change as a function of time. They're going to be time-varying functions. And then from here on out, I'll probably just drop the parentheses t, because we all know that they're going to change with respect to time. Now, mathematically speaking, not talking any physics now, just pure mathematics, if you pick up your old dynamics book from your freshman year or sophomore year, for those of you that even take dynamics anymore, in the back, there's all these formulas that tell you how to get velocity from a position vector in any arbitrary coordinate system and the acceleration. And so I'm just going to give you what the back of the book says for the cylindrical coordinate system. Velocity vector in terms of r and theta is given by r dot, r hat, the unit vector that always points away from the origin, plus r theta dot, theta hat. That's the orthogonal unit vector, theta hat, that always points in the direction of increasing theta. The dots, of course, is just first derivative with respect to time. And you'll notice that we didn't just take r dot, stick it on the r, and theta dot, stick it on the theta. That's something that my undergrads make a mistake of whenever they're doing vector operations in my electromagnetics class. You can get away with that kind of horseplay in Cartesian coordinate systems because x hat and y hat and z hat are fixed with respect to your point of observation. No matter where you go in life, in the Cartesian coordinate system, x, y, and z always point in the same direction. So they're constants. One of the double-edged sword about when you move into coordinate systems like the spherical coordinate system or the cylindrical coordinate system or whatever crazy coordinate system some math PhD has invented to solve a problem and escape his PhD program, those coordinate systems are formulated in a way to simplify some geometrical aspects, but they often complicate other aspects. They almost always complicate taking derivatives, because if I take the derivative of r on the r hat and theta here, these r's and thetas change depending on my points of observation. So I can't just take the derivative. It's not even dimensionally correct. Like theta dot is radians per second. I need something that has units of meters per second in order to be a bona fide velocity. And so that's why I got to multiply those two things. Acceleration is even uglier. If you want to take the next derivative with respect to space, and you look in the back of your dynamics textbook, you get this crazy expression. R double dot, second time derivative with respect to time, of r with respect to time, minus r theta dot squared, stick it on the r hat, and then finally, and that's all on just the r hat. Then on the theta hat, you have this component, r theta double dot, second derivative of theta with respect to time, plus 2 r dot theta dot on the theta hat unit vector. Okay, so that's it. I don't think I made any boo-boos. Now, how do we use this to figure out what the orbit should be? Okay, so going back over here, let's make a more formal treatment. My acceleration vector is going to be equal to minus GMP over r squared, stick it on the r hat, plus 0 theta hat. How did I get this? Okay, first of all, we're going to leave the textbook physics world and enter into satellite communications. What am I orbiting? Planets, usually. So I just call this m sub p. That's going to be the mass of the second object. Now it's the mass of the planet that's exerting gravitational forces on the spacecraft. There's your Newtonian's constant, r squared, minus. It always points towards the origin. If we are going to place our planet at the origin, the centroid of the planet is at the origin, then I have an r and a theta that traces out a trajectory around there, and it has to follow this equation. Newton's force always points inward, so I conveniently align myself with the cylindrical coordinate system. There are no tangential forces, so I'm going to assign that equal to 0. And this gives me a great way to solve the system now, because this is the mathematical definition of my acceleration vector. All I have to do is equate the r hat components and the theta hat components. So I have basically two coupled differential equations now that describe the motion of this system. We have r double dot minus theta dot squared equals minus GMP r squared. That's equation number 1. And then finally r theta double dot 2r dot theta dot. The sum of those is equal to 0. Any questions so far? So really, the first week or so of class is just solving that system right there. It's pretty simple. It's pretty simple. And then also describing how does real life deviate from this? Because real life is never this clean, unfortunately. I think orbital mechanics is about as clean as anything gets scientifically to solving a pristine differential equation system. But even there are some irregularities. Now we are going to start by solving this for the simplest possible system, okay? The simplest possible system, the circular orbit. The circular orbit. For circular orbits, we have one beautiful condition. R is equal to a constant. A satellite in a circular orbit always stays the exact same distance from the centroid of the planet. And armed with this really simplifying assumption, if we are to have a circular orbit, then we can derive some pretty simple conditions for what that orbit has to satisfy based on this dynamic set of equations. So, well, let's go ahead and take a look right here since we have them up. R dot double dot. If r is a constant, every time you see r double dot and r single dot, you know those are 0, right? So those go away. And every place, not the whole thing, just that part. And every place that I see a little r, I can just make this into a constant. There we go. There we go. So now, I have some interesting formulas that describe the conditions that I have to have for satellites. First thing, there is no angular acceleration. V theta, which is the theta component of velocity, you'll see from the second equation that theta double dot is equal to 0. Divide through by r, theta double dot is equal to 0. So there's no acceleration. The angular sweep must always be constant for a circular orbit. We can get what that angular sweep is from the top equation. I divide through by r, take away the negative signs, and take the square root. That gives me r theta double dot. When I plug in that top equation for theta double dot, that gives me the square root GMP over r. One of the most valuable equations you'll learn in this class. Velocity of a orbiting spacecraft is equal to the square root of Newton's gravitational constant times the mass of the planet divided by the distance away from the planet. And so there's an inverse relationship. The farther you move the satellite away from the planet, the slower it travels to remain in a stable circular orbit. So it travels slower, and it has a longer diameter around the circle to travel, which means once you get to a certain, as you go out further and further, you really slow down what we would call the orbital period, the time it takes the spacecraft or satellite to make an entire sweep in orbit. So, trying to think about we'll mention this when we get to my favorite calculation in the class, which is coming up in a few minutes. Let's write an expression for orbital period because it'll help us out later. Orbital period, how long does it take a spacecraft to make one revolution in a circular orbit? T, we always give it the value T. It's the orbital circumference that's basically 2 pi r, divided by orbital speed, which we have here as this expression. So if I plug those in, I get 2 pi r to the 3/2 divided by the square root of g and p. So you can see that as I move farther, there's a more than linear dependence on the distance away from the planet and the orbital period. The only way to speed it up is to orbit around something that has more mass. This is why when you go to Jupiter and do a science mission, the orbiting spacecraft is whipping around that massive planet very quickly, much quicker than it would be on Earth or one of the other planets. Now, I should mention this point too. I always work these problems in terms of Newton's gravitational constant and the mass of the planet. However, as sort of a legacy from the 1700s or wherever, there are a lot of people that record orbital information in terms of mu, which is called Kepler's constant. Because this is how he formulated his original orbital mechanics. But they will say for each planetary system or each orbiting system has its own Keplerian constant mu, which is really just the product of the mass times g. So you'll see tables of mu's and equations in terms of mu's, I think a little in your textbook and a lot in a lot of other textbooks. And they really mean the same thing. It's just a different convention for writing your formulas. I try to stick with this one. Okay. So far, so good. Now, let's work an example. I can do this. I've never had a classroom where I could do this before. Good. So here's our example problem. How far up do we launch a satellite so that it orbits at the same rate of rotation as the Earth, as the Earth's surface, basically. There is a magic altitude that you can launch a satellite, a magic radius, where the spacecraft will rotate through its orbit at the same rate as the rotation of the Earth. And if you do that, then from the vantage point of somebody, a fixed observer on the Earth, you can look at that satellite and it hangs perpetually in the same point at the sky all the time. And you can hammer in a little gray dish and watch direct TV and not have to move it, right? Because that's ultimately what we want out of this. So what is that? That's one of the most important calculations we'll make in this class. We're going to take the answer to this and probably use it until the end of the class period with all the other systems that we talk about. Let's go ahead and calculate it. But there's a little bit of nuance with this calculation. Okay. I already gave you the formula on the previous page. T is equal to R over to the 3/2 power. And then, let's see, doesn't I have a 2 pi there? 2 pi square root of GMP, Kepler's constant. So all I need to do is figure out what should the period be, and I solve for R. The mass of the Earth, well, that's easy. We've estimated that to be 5.974 times 10 to the 24 kilograms. Very heavy planet. And of course, I know this is about 6.67 times 10 to the negative 11th, so I've got that. All I need to do is solve for R. The question is, what should I put here? Well, how long does it take the Earth to do one rotation? 24 hours. That is a trick question. It's a trick question. 24 hours is what a solar day is. We want a sidereal day. A sidereal day. That's a tricky. Why? Okay, let's say, what's the difference? Okay, here's the sun, and here's the Earth. And I'm looking down at it, so there's the North Pole, and it's turning around like this. Now, your perception of the 24-hour day is based on the fact that in 24 hours, the sun more or less is going to be in the exact same spot in the sky as it was. The problem is the entire time you're doing that, you're actually revolving around the sun. So that when you get over here, like the next day, you actually have to add about 4 minutes to twist so that the sun gets back to where it is in the sky, because you're now looking at it from this angle. So it's got to twist an extra little bit more. And you add that up. In fact, if you multiply 4 minutes by 365, you get 24 hours effectively. So a sidereal day, the actual, in an absolute universe, looking at the Earth, the amount of time it takes to make one rotation is actually, here's the magic constant, 23 hours, 56 minutes, 4.09 seconds. Or if you want to put it all in seconds, 86,164.09 seconds. And this is a sidereal day. Okay, any questions so far? So now let's plug this in. The magic distance, if you use this sidereal formula, is an R of 42,164.17 kilometers. That's measured from the center of the Earth. So always keep that in mind. I always specify what I want in the problem. There's a difference between reporting an orbit in terms of altitude versus absolute radius. And I'll specify which one I want. And I don't care which number you give me as an answer on a test or a homework, as long as you specify what it is. This leads to really silly answers on tests, like orbits that, like where the spacecraft has to plow through magma in order to complete the orbit, because they're confusing an altitude with a radius. This is the radius. The altitude, the Earth's radius is about 6,380 kilometers. So that would make the altitude about 36,000 kilometers if you're reporting from the surface of the Earth. So you'll see that number bandied about in papers and textbooks. But that's the magic height. If you put that spacecraft up at 42,000 kilometers from the surface of the Earth, it will hang in the sky at the exact same point. Well, okay, there are 3 conditions, actually. If you make the orbital period a sidereal day, you have a geosynchronous orbit. Means the orbit will repeat itself every day, but unless it's a circular orbit, which is the condition that we just found, we derived that equation using circular orbit, so we got a circular orbit answer for the radius. And it has to be equatorial, aligned with the equator so that it tracks around. If you do those three things, geosynchronous, equatorial, circular orbit, then you have a geostationary Earth orbit. And that's three conditions. The orbit has to be circular, geosynchronous, 1 sidereal day, and it must be equatorial. It cannot be inclined. There are actually a lot of useful orbits that are geosynchronous, but not the other two. Or maybe geosynchronous and circular, but not necessarily equatorial. They would not be geostationary. They would trace out a path in the sky or beyond the horizon during the course of the day that would repeat itself every day, but would not be fixed. Why would you want to do that? We'll learn why we want to do that in a couple lectures. There's actually a lot of degrees of freedom and interesting design parameters for those types of satellite systems. Okay. Now, that number, that magic number of 42,000 kilometers, gives us a really nice taxonomy for talking about spacecraft that orbit the Earth. So let's say I've got the Earth down here. I'm looking out, down from space. Here's my Earth. We have these demarcations, largely based on this number. So let me write it in terms of an altitude here. This is 36,000 kilometers above the Earth. Imagine this is a cut of a sphere that encapsulates the Earth. This over here is this line that I've drawn down here. Imagine this as a 1,500 kilometer encapsulant of the Earth. If a satellite is below this line, we call it a low Earth orbit. Or if you are a seasoned satellite engineer, you just call it a LEO. If you are circular up here and you're equatorial, this marks the boundary of geostationary Earth orbit. Geo. If you are in this region in between, you are at medium Earth orbit. And if you are beyond this, we call this high Earth orbit. Okay. So those are the three classifications. Low Earth orbit, most of our spacecraft either go one of two places. They get put in a circular geostationary Earth orbit, or there's a ton of them just zipping around in all directions in low Earth orbit. Why are there so many in low Earth orbit? Well, there are a lot of applications that benefit from low Earth orbit, things like surveying and photography and all this other stuff. And also, it's a very inexpensive orbit to launch something into. Launch costs are largely dictated by how much mass are you putting into orbit and how high the orbit is. Things get very expensive once you get beyond low Earth orbit. Low Earth orbit is the lowest possible orbit, so let's put all of our satellites in there. You can get them talking to one another and provide global coverage just by launching a constellation into low Earth orbit rather than sending it all the way up to geostationary Earth orbit. Now, there are some applications where geo is preferred. You want that fixed position, for example, in the sky, that all the TV users or all the dish owners or the feed, people that are trying to intercept your feed can tune their dishes to, turn them to, and relay a signal. And there are some applications, they're not quite as common, but there are plenty of applications for medium Earth orbit. GPS, for example, all GPS satellites in the navigating constellation are in medium Earth orbit. What's the trade-off there? Well, they're a little bit more expensive to launch than in low Earth orbit. What do you get by going up here to medium Earth orbit that you don't necessarily have for a satellite zipping around down here? What?
So get more time.
Slower speed, so more coverage time. Yeah. Also more coverage area, too. Both of those are good reasons. You see more of the surface of the Earth the higher that you go. I mean, if you went to infinity, you'd see 2 pi sterradians of the Earth. These guys down here, they only see, if they beam a signal, no matter how wide the antenna gets, they're only going to cover a certain portion of the Earth. And they're probably only going to be in view for 10 or 15 minutes, depending on what part of the Earth and exactly how high you put them. You might have even seen satellites like this on a really clear night, not in Atlanta, but like if you go to an island somewhere, you can look up at the sky and you can see fast-moving, faint light. It looks, you could almost mistake it as a really high-altitude airplane, but they're usually fainter than that, and they zip across the sky. You can see, they last they'll be in the sky for 10 minutes if they're going from horizon to horizon. You almost never launch anything useful to high Earth orbit because there you've got the worst of all the worlds. It's not stationary with respect to an observer on the Earth. It's the most expensive place to launch because you got to get overcome the most potential energy. And so what you find is that high Earth orbit users are a lot of the scientific measurement missions use high Earth orbit. If you're studying the solar wind, for example, or maybe you're, observing the Earth's magnetosphere or something like that, you'll find NASA launches stuff into here, but commercial ventures tend to avoid high Earth orbit. And so if you could look if you did a scatter plot of the Earth and where all the orbits are, you'd find just the whole low Earth orbit area is just littered with satellites. Literally littered. And then in medium Earth orbit, you have your occasional navigation satellites, a few other applications. And then there's this dense band. Like over here, you got North America, a lot of the satellites up here in geostationary Earth orbit, and not so many over here. And then Asia, you pick it up again, and Europe. Nobody watches DirecTV over the Pacific, so there's not much out there. And that's kind of what it looks like from space using this taxonomy. Okay. Any questions so far? Perfect understanding? Oh, yeah.
Geosynchronous orbits are?
So a geosynchronous orbit, the question is to explain what a geosynchronous orbit exactly is. It's any orbit, circular or otherwise, equatorial or otherwise, that has a period, any orbit about the Earth, that has a period of 1 sidereal day, 23 hours and 56 minutes. As long as you satisfy that, it doesn't matter what the shape of the orbit is, it's a geosynchronous orbit because it will repeat itself exactly 1 sidereal day. The sky track, if you can imagine it this way, the sky track, if you could see the satellite at all times, the path that it traces out in the sky always closes in on itself. If it was not geosynchronous, it would do its thing, and then the next day it would be at a different spot, and then it would do another thing, and it would change from day to day with respect to the observer instead of just minute to minute. Now, there are some other types of synchronous orbit. For example, there's something called a sun-synchronous orbit, which again means that the satellite may do multiple passes, but during the course of a day it will repeat itself. I forget what the exact radius is for a low Earth orbit in a sun-synchronous orbit. I don't have that example worked out in my notes, but there's a lot of different things you can synchronize an orbit to. Some are kind of semi-synchronous. They repeat themselves every half days, every half of a sidereal day. I'll show you an example later on when we study elliptical orbits of an orbit that does that.